Namaste students, thank you so much for joining us. I hope you all are having a good evening and that you had a good day at school today. Yes, I know I'm addressing some of the questions in the chat box. All the recordings will be uploaded on Saturday, which is tomorrow. All right. So all the sessions that you have missed, in case you have missed and you would like to view them, you can log into the website tomorrow, enter your spot ID, and you can access the recordings. We shall begin the program at 5 o'clock. We're just waiting for more students to join in. We will also be sharing the attendance sheet in a short while. So it is a request for all of you to mark your attendance. I'm sure you're familiar with the process now. So kindly ensure that you fill in your attendance for today's class. As usual, it will be a Google form that you will have to fill up. Thank you. Good evening to the students who have just joined us. We shall begin our program shortly. Thank you for joining us today. So with your permission, can we begin the program? All right, sir. Thank you. Good evening to all our spot qualifiers. Welcome to your third session of the VSSF Spot Virtual Classrooms. We're so happy that you have joined us for this session today. As you are aware, we will be moving on to the rules very quickly. Please ensure that you actively participate in the session, because questions from this session could be asked in your final exam. Ensure that your microphones are always on mute except when asked to be unmuted by the host. And with regard to the chat box, it is a humble request to kindly refrain from posting the same message repeatedly on the chat box, because if you post it once, we will see it. If you keep posting it over and over again, we might tend to miss out the other questions because it becomes more difficult to access everything. So kindly refrain from bombarding the chat box with messages that are not related to the topic at hand. All right, because otherwise we might have to restrict your participation, and that's not something that we'd like to do. So kindly ensure that if you have a question or a query, post it once in the chat box, and we will try and address as many questions as we can, given the amount of time that we have at the end of the session. Yes, so that brings us to our topic for today, which most of you have been interested in, excited about. It's atomic energy. Now, the concept of an atom has existed for many centuries, right? But in recent years, when we think of atomic energy, we start understanding it as something to do with enormous power generated by atomic energy, or otherwise commonly called nuclear energy. And in the years just before, and perhaps even if I can say World War II, nuclear research focused mainly on the development of defense weapons, right, and machinery. So when you think of atomic energy, you sort of correlate it with defense mechanisms or weaponry. However, later scientists concentrated on more peaceful applications of nuclear technology, and an important aspect in the use of nuclear technology is the generation of electricity, which is something that none of us can do without, right? So after years of research, scientists have successfully applied atomic energy to many other scientific, medical, and industrial purposes. I'm sure that you are going to enjoy your session today, because I would like to very humbly, with utmost humility, welcome our keynote speaker for today, Dr. Swapnesh Kumar Malhotra. Sir, it is an absolute honor and privilege to have you with us today. I would quickly, very briefly, like to introduce you to our audience. Now, it's not very easy to introduce Dr. Malhotra because there are pages and pages of work that he has done for our country, and it is impossible to read it all out for you, but I will try my best and put it in a nutshell. All right. So Dr. S.K. Malhotra was the previous head of the Public Awareness Division, Department of Atomic Energy, Government of India. Earlier to that, he superannuated from the Department of Atomic Energy as Outstanding Scientist and Head, Public Awareness Division. After his post-graduation in chemistry from Agra University in 1976, he joined the Bhabha Atomic Research Center in Mumbai. After a year of training in the nuclear science and technology, he joined the Bhabha Atomic Research Center as a scientific officer. For more than 2 decades, he was engaged in the research and development of heavy water, an important nuclear material for the Indian nuclear power program. His major fields of interest were hydrogen isotope separation, fractional distillation, cryogenic distillation, electrolysis, metal hydrogen system, and mass spectrometry, and the list goes on. He was involved in the technology transfer activities of the Bhabha Atomic Research Center for a couple of years. Since 1999, as the head of the Public Awareness Division of Department of Atomic Energy, he was responsible for planning, overseeing, and assessing the entire outreach program of the department. He has produced a number of documentaries. He was also responsible for the conceptualization, design, and production of various publications for the Department of Atomic Energy. He's also served as an expert with the International Atomic Energy Agency for assessing and advising them on their public information program. Why we would love to have Sir with us today, apart from all the laurels that he has brought for himself and our country and the field of atomic energy, is because he loves interacting with students. He's very fond of interacting with students and sharing his passion with them. As you can see, there are so many awards and recognitions that Sir has to his name. You can quickly go through it because we will run out of time if I have to read out everything. Sir, we welcome you wholeheartedly for our session today. Thank you so much for joining us. Over to you, sir.
Thank you. Thank you, madam. And thank you, children. And I welcome you to this exciting session with me on nuclear power. So as madam just now told that, am I audible clear?
Yes, sir, you are audible.
Okay. So as she told that though atomic energy was introduced to the world in a destructive manner, I think she did not say it explicitly, but I am telling you, yes, it was introduced to the masses through devastation that happened at Hiroshima and Nagasaki. But after that, this is not something new. It is not that only with atomic energy it has happened. Every time we have made a discovery, we have first made only destructive use of this. See, I will tell you from the early history, the primitive man, when he graduated, the primitive man graduated to become the Stone Age man. What was the difference? He, from primitive, he entered into the Stone Age. He started using stones. Now he was using stones for what? First, the early man was using stones for hitting each other. Because before that, they used to fight individually with each other, over some piece of another animal or something, piece of anything. They will fight with each other, but they have to fight individually with each other, wrestling or boxing. But then they discovered that if they pick up a stone and hit it to the the opponent dies or at least gets badly injured. So they discovered the power of stone. So what did they do with the stone? They started using the stones for harming each other. And that process is going on even today. Even I think, if I can remember, when the president of USA had come, on the same day in Delhi, stones were pelted and Delhi, a part of Delhi was brought to a standstill. So first use of stone we made as a weapon. Later on, they learned that, okay, if we uh, pile up stones above each other and we can make a wall, and such four walls we can make, then we can put a roof over it, then we get a beautiful, a house to live in. So this came much later. Much later, they built they learned the use of concrete. They made bricks, and they learned to make flyovers. They learned to make dams with the same stone. But please remember, the first ever application was as a weapon. And I think I can go on. When the metal age came, in metal age, copper, brass, iron, all this came. Again, the first use was in making knives, in making swords, in making other weapons. Much later only they started learning that metals can be used for making vessels, for making beautiful statues, and for reinforcing the buildings which were being made with bricks and stones. So I think I will not waste more time on this. So it has been a tendency of the mankind to discover something and make a bad use of it, harmful use of it. Same thing happened with atomic energy. Same thing happened with TNT, trinitrotoluene, which was discovered by none other than Alfred Nobel. And what was the first use? It was used to kill people, and it was used to kill thousands and thousands of people. Lot of money he earned by selling this TNT. And later, after killing so many, he realized, oh my God, what I have done. And then of course, the good senses prevailed, and all that money which he earned basically by killing people, he deposited in some bank, and out of the interest of that money, all the Nobel prizes are being are being given. So it has been nothing different in the case of atomic energy also. First, nuclear weapons were made, but then in 1953, even I was not born at that time, the president of USA, Eisenhower, at that time, he said, after killing, mass killing of people in Japan, he said, no, we should use nuclear power for peace. So a program called Atom for Peace was discovered, was initiated, out of which International Atomic Energy Agency was established as a part of the United Nations in 1957. And of course, India is a member of it. And of course, then rest is history. So today, atomic energy is being, you imagine a field and atomic energy is being used in that. Be it generation of electricity, be it water, be it agriculture, be it food, uh, be it your industry, and be it healthcare. In healthcare also, just to give you a recent example, the very popular RT-PCR test for COVID-19. I think all of you must have heard the name RT-PCR test, the most trusted test for COVID-19. Okay, it is actually a nuclear derived technique. It was initially developed with radiation in it, with radioactivity in it. But today, the technique today does not have any radioactivity in it. Later on, it was developed, and instead of radioactivity, nowadays some fluorescent dyes are used in that. So what I am trying to tell you is, you name a field, and atomic energy is there helping the mankind in that. Today, I will be restricting myself only to generation of electricity using nuclear power. Okay, so let us move to the topic. As such, I have given the title Atoms, Radioactivity, Radiation, Fission, and Nuclear Power. So let us move ahead. So can I have the next slide? Oh, yes. So let us start with, let me give you a concept of from very big distances to very, very small distances. See, when you happen to hear a lecture on astronomy or on space science, you will hear big, big distances. You will hear about the interplanetary distances, the distances of the planets from the sun, and the size of the Milky Way, size of the black holes. You will hear very large distances, and then it will go to light years. That is the distance covered by light in 1 year. Okay. And when you come to atomic energy, you will hear very, very small distances. Okay. Which are even smaller than the thickness of your hair. So just to give you a feel of distances, I have made this slide. So let us start. I think many of you will be knowing some of these distances. So the distance between Earth and Sun is 150 million kilometers. Now, as all of you know, the international standard unit of distance is meter. So I'm converting everything into meter in the third column. So 150 million kilometers is the distance between Earth and Sun, which is 1.5 into 10 to the power of 11. So that means you write 15 and 10 zeros in front of that. Those many meters is the distance between Sun and Earth. Then Earth to Moon is 384,000 kilometers, which is about 3.84 into 10 to the power of 8 meters. Okay. Then now let us come to something practical. We are seeing everything. So the average human height is 5 to 6 feet, which is about 1.5 to 2.0 meters. Thickness of human hair is about 0.1 millimeter. That means 10 to the power of minus 4 meter. Size of bacteria is 0.2 to 10 micrometer. Micro is 10 to the power of minus 6 meter. So 0.2 to 10 micrometer, that which translates to 2 into 10 to the power of minus 7 to 100 into 10 to the power of minus 7 meters. Size of virus. Nowadays, of course, the whole world is suffering because of the virus called COVID-19. So, size of the virus is 20 to 400 nanometers. Nano is 10 to the power of minus 9. Okay. So, so size of the virus is about 2 into 10 to the power of minus 8 meters to 40 into 10 to the power of minus 8 meters. Then we come to size of atom, which is ultimately I wanted to give you the feel of the size of an atom. So it is 0.1 to 0.5 nanometer, or it is also popularly known as 1 to 5. See, 10 to the power of 9 minus 9 meter makes 1 nanometer, but 10 to the power of minus 10 meter will make 1 angstrom. So the same thing, which is 0.1 to 0.5 nanometer, becomes 1 to 5 angstrom. Or if you convert it into meters, then it is 1 into 10 to the power of minus 10 meter to 5 into 10 to the power of minus 10 meters. Now let us come to the part of that atom, size of the nucleus, which is 1.5 to 15 femtometers. Femto means 10 to the power of minus 15. So size of nucleus is 1.5 to 15 femtometer, that is 1.5 into 10 to the power of minus 15 to 15 into 10 to the power of minus 15 meters. So that was just to acquaint you with the, you can imagine what is the small size of atom. So now let us come to the next slide where we tell more about atom. So as all of you know, all objects, living or non-living, they consist of atoms. An average adult human being is made up of approximately 4 into 10 to the power of 27 atoms. That means you write 4 and put 27 zeros in front of 4. So those many atoms of carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, and many more. Okay. Now, just now in the previous slide, I told that size of the atom is about 10 to the power of minus 10 meter, and size of nucleus, which is the most dense part of the atom at the center. If you compare it with the planetary system, so our Earth planetary system, then in the center we have sun and we have the planets orbiting all around. So similarly, here the nucleus is there, and around the nucleus, electrons are revolving around that nucleus. So that nucleus is of the size of 10 to the power of minus 15 meter. So that means 1 lakh times smaller than the atom. So what the information does it give? That most of the atom is actually empty space. It is just like our space. In space, we have so many stars, we have so many galaxies, we have so many suns, we have so many planets. But actually, if you look at the space, most of the space is empty space. So similarly, in case of atom, most of the space within an atom is empty space. And another information is because, as I will be telling you about neutrons and protons. So neutrons and protons, which form the nucleus, they are very heavy as compared to the electrons. I'll be telling you about their masses. So the entire mass, practically entire mass of the atom is present in the nucleus. So very small volume of the atom, but practically entire mass of the atom is within the nucleus. Okay. Now, as I just told, that nucleus consists of protons and neutrons. Protons are positively charged particles. We have just, we have given, we have made a unit of electricity in such a way that we say that a proton carries +1 charge. Okay, while neutron does not have any charge. And then around the nucleus, there are electrons revolving. They have -1 charge. So +1 charge to proton and -1 charge to electrons. But anyway, we will come to electrons a little later. So let us talk about about the nucleus only. So within nucleus, you have protons. Each proton has a +1 charge, and mass of every proton is 1.672 into 10 to the power of -27 kilogram. Similarly, neutrons, as I already told, neutrons have no charge, zero charge. Okay, they are neutral particles, and their mass is, they are slightly, very slightly heavier than protons. So mass of a neutron is 1.674 instead of 1.672, which is the mass of the proton. It is 1.674 into 10 to the power of -27 kilogram. Okay, then we come outside the nucleus in the orbits. Electrons are orbiting, and each electron has a -1 charge. So each electron will neutralize the positive charge of one proton. Okay, so for every proton inside the nucleus, there has to be an electron outside the nucleus, so that the atom is supposed to be neutral. It is not supposed to carry any charge. If an atom is carrying a charge, then it will become an ion, which you must have studied or you will study. If you remove an electron from an atom, it becomes a charge. Or if you add an electron to the atom, then also it becomes a charge. If you remove an electron, it will become positively charged. So atom will become a positive ion. If you add an electron to the atom, it will become negatively charged particle. So that means it will be a negative ion. Okay. So as such, electrons have -1 charge, and their mass is, look, so small as compared to proton and neutron. It is 9.1092 into 10 to the power of -31 kg. Okay. Now, as I already told, electrons are negatively charged. Their mass is this much, and they revolve around the nucleus in the orbit. And that makes the atom stable. In an atom, naturally, number of electrons has to be equal to number of protons. I already told you, because each electron is going to neutralize the +1 charge of a proton. So their number has to be equal. Okay, thus so that atom is electrically neutral. Okay, so much so about atom. Now let us move. Next slide. How do you identify an atom, a particular atom? You know, in periodic table, you see there are various elements. So how do you identify atom, that this is atom of hydrogen, this is atom of uranium, this is atom of lithium? It is identified with their atomic number. That means by the fact that how many protons are there inside the nucleus. That decides the identity of the element, that which element it is. So atomic number of an atom is the number of protons in its nucleus, or the number of electrons orbiting around the nucleus. As I already told you, number of electrons has always to be equal to number of protons. Okay, so as I already mentioned in the beginning, an element is defined by its atomic number. So for example, when you say hydrogen, now any atom of hydrogen, any isotope of hydrogen, the atom of hydrogen in India, atom of hydrogen in United States of America, or in the ocean, it will, the atom of hydrogen will always have atomic number 1, because it has only one proton in its. Now there is another quantity, which is mass number. mass number of an atom is the total number of protons and neutrons in the nucleus. So as I already told you, inside a nucleus, in addition to protons, there are neutrons. So you add up the number of protons and neutrons. That will be the mass number, because that will decide how heavy the atom is. So just to give you an example, let us take the case of hydrogen. Its atomic number is 1. Its mass number is also 1. Why? Because I'll tell you. So number of protons in the nucleus is 1, because because atomic number is 1. Okay. Then number of electrons will be 1, because for every proton there has to be this thing. And how many neutrons? 0 neutron. Okay, because the atomic number and mass number is same, that means there are no neutrons. Now let us take the case of helium, where the atomic number is 2, but the mass number has become 4. So what does it tell us? It has 2 protons in the nucleus, it has 2 neutrons in the nucleus, and of course 2 electrons revolving around the nucleus. And the story goes on. Let us come to see, because in case of nitrogen and oxygen also you will find the same thing. You will find that the number of protons and number of neutrons is equal. But when atoms become heavy, so I have given you one example, uranium. So, and uranium is an element of interest to us. So uranium, the atomic number is 92. But the most abundant isotope of uranium found in nature, its mass number is 238. Okay. So what information does it give? That each nucleus of uranium will have 92 protons, 92 electrons will be revolving around the nucleus, and it will have 238 minus 92. That means 146 neutrons inside it. Okay. So this is the concept of atomic number and mass number. This is very useful. In atomic energy, if we do not know this, we cannot go ahead. Next slide, please. So now we come to the concept of isotopes. Now I told you that each element is identified by its atomic number, but the same element can have different types of atoms. For example, if it is atom of hydrogen, it's, as I told you, that its atomic number has to be necessarily 1. Okay, but if it is the normal hydrogen, which we call as hydrogen, actually in science we call it protium. Its atomic number is 1 and mass number is also 1. So no neutron. But then there is another isotope of hydrogen whose atomic number has to be 1 anyway, because it is hydrogen, but its mass number is 2, because it contains 1 neutron. It contains 1 proton plus 1 neutron in the nucleus. So it is called deuterium, or it is also known as heavy hydrogen. So they are isotopes of each other. Then there is a third isotope. You add another neutron to that nucleus of original hydrogen. Already 2 are there, because originally there were no neutrons. You added 1 neutron, it becomes deuterium. You add another neutron to it, so now it will have 1 proton and 2 neutrons. So its mass number will become 3. Of course, atomic number will remain as 1 only, but mass number will become 3. Okay, so they are the 3 isotopes of hydrogen. One is protium, one is deuterium, another one is tritium. Okay. Now, see, in such cases, if you take an element, as you know, all atoms of gold, they will exhibit the properties of gold. So you know what is the melting point of gold, you know what is the density of gold, you know, I mean, in case of oxygen or in case of hydrogen, you know their physical properties, like density, melting point, boiling point, etc. So these physical properties will change a little bit because of that mass number being different. The physical properties will change a little bit. Okay, while chemical properties of an element essentially remain the same, whether it is this isotope or that isotope. So chemical properties of all isotopes of an element are the same, but physical properties, there is a variation. Okay, just to give you an example, see, if you make water from protium, so H2O, pure water, pure water, then its melting point is, as you know, is 0 degrees centigrade, and its boiling point is 100 degrees centigrade. But if you replace the 2 atoms of hydrogen by 2 atoms of deuterium, so it becomes a D2O, heavy water. We call it heavy water. That heavy water, the boiling point is 101 degrees centigrade. Okay, so it has slightly changed. So physical properties are slightly different of isotopes, while chemical properties are essentially the same. Now, these are some examples. Next slide, please. Some examples of isotopes. I already told you about hydrogen isotopes, the 3 isotopes. Then carbon, 3 isotopes, 12, 13, 14, out of which carbon 12 is the bulk isotope found in nature. And 13 and 14 are also found in nature. Oxygen, 16 is the normal oxygen we know. And then you have oxygen 17 and also oxygen 18. In case of uranium, the most abundant isotope found in nature is uranium-238, while in the nature only there is uranium-235. And then there is a man-made isotope, uranium-233, which is not found in nature, but we make it, as I'll be telling you. So these 3 isotopes of uranium, actually there are more isotopes, but I have listed only 3. Okay, so these are examples of certain isotopes. Now, next slide, please. Now we differentiate between the isotopes. We call it stable and radioactive isotopes. So I am introducing you to the concept of radioactivity. So what are stable isotopes? They do not decay. They are, they are sort of permanent. They are not going to be destroyed, and no radiation comes out of them. In stable nucleus, the protons and neutrons, they are bound together by nuclear forces. They are bound together by very strong nuclear forces. So you normally will not be able to break this atom. So this atom is a stable atom. On its own, it will never disintegrate. It will never break. It will not give out its particle. It will not allow another particle into it. So it is normally, that is why it is called a stable isotope. Deuterium also is a stable isotope of hydrogen. But when the third isotope, tritium, there is 1 proton, and now there are 2 neutrons. So there is an imbalance. So they are not very tightly bound with each other. So the tritium atom doesn't remain stable. It starts giving out radiation. Okay. So then it is known as a radioactive isotope. So radioactive isotope of hydrogen is tritium. Similarly, they release their energy. You know, their energy is high. They are unstable. So their energy is high. So they release energy either in the form of particles or as electromagnetic radiation. That I'll be telling you later. This process is called radioactive decay. And so examples are shown here: tritium, carbon 14, cobalt 60, iodine 131, iodine 125, uranium, thorium, plutonium, etc. are examples of radioactive isotopes. Okay. Generally, they emit 3 types of radiation. They can decay. You know that radioactive decay can occur in 3 modes. So from a nucleus, which will naturally happen in the case of very heavy nucleus, a nucleus will decay by an alpha decay. We call it alpha decay. Alpha decay means one nucleus of helium will come out of that nucleus. So mass number 4 and atomic mass 2, that kind of particle. So alpha particle is nothing but the nucleus of helium, the element helium. So in the helium atom, if you remove both the electrons, there are 2 electrons, then it will become the helium ion. Okay, so only helium nucleus. There are no electrons now. So helium nucleus, which will have atomic number 2 and mass number will be 4. Okay, so that is called as alpha particle. So one way of, so materials like uranium, thorium, etc., they undergo alpha decays. Okay, then there is beta decay. Beta decay is nothing but an electron coming out of the nucleus. Now you should ask me a question that I told in the beginning that the electrons are outside the nucleus. Then how is the electron coming from the nucleus? It is basically conversion of a neutron into proton. Okay, a neutron is getting converted into a proton. So what is happening? That means neutron is getting converted into proton means a positive charge is generated. So an equivalent negative charge has to be generated. So when neutron changes into proton, it also releases one electron. Okay, that electron which comes out of the nucleus is known as beta particle. Okay, so that is also called, that radiation is known as beta radiation. And third is gamma radiation. Gamma radiation is just like X-rays, ultraviolet. It's very, very energetic. I mean, much more than ultraviolet. It is of the range of X-rays, or sometimes it will be even more than X-rays. So its energy is very high. Okay, so this is gamma particle, which is an electromagnetic radiation. It does not have any particles. Now, can we have the next slide? So now here, next slide, please. So here in this slide, I am explaining the event during which an unstable atom emits its excess energy. That radiation comes out either alpha, beta, or gamma. That process is called radioactive decay. Light nuclei like tritium or carbon-12, they normally only by one decay they will become stable. So an example is given here. This is tritium, H13. See, always the atomic number will be written to the left of the nucleus at the bottom, and the mass number will be on the top, just above the atomic number. So H13, it means it is tritium. It is the isotope tritium of hydrogen. So this decays. It decays. So it gives an electron. And now see, as you know, tritium contains 2 neutrons. So out of the 2 neutrons, the 1 neutron gets converted into proton. Okay. So that is why the mass, the atomic number from 1, it becomes 2. Why it becomes? Because 1 neutron has got converted into proton. So now the new nucleus has 2 protons inside. But that means its atomic number is 2 now. And that 2 belongs to helium. So it has become a helium particle, but with a mass number 3. So another isotope of helium, which is not the natural helium. Natural helium, that mass number is 4. But here it is mass number 3. Okay, and a beta particle has come out. But in case of very heavy nuclei like uranium, thorium, etc., by one decay, nothing will happen. You must have seen an advertisement in the TV. I will not name the product, but about a product. Earlier times, this ad used to come. Ek se mera kya hoga? Huh? That one is not enough for me. So very heavy nuclei, when and they are unstable, then they decay. multiple number of times to become stable. So one example is given here, that how uranium first decays into thorium, which then decays further, and after so many decays, it finally becomes a stable isotope of lead. Okay, so these are called as the decay series or the decay chain. Okay, so all heavy elements will show these multiple decays. So they will have a decay chain. Now, and on the earth, so many various isotopes. So for example, so many isotopes of thorium, so many isotopes of uranium, so many isotopes of so many other elements are found. That is because of all these decay chains. It is happening in naturally, this decay is happening. So you find, and it has been happening for millions of years. So you find various types of isotopes. Some of them are radioisotopes, others are stable isotopes. You find them on the earth, you find them on the moon, you find them on other planets also. Next slide, please. So here I have told about the three types of radiations. The alpha radiation, as I already told you, consists of alpha particles, which are nothing but nucleus of helium. Each alpha particle contains 2 protons and 2 neutrons. Its mass number is 4 and it has +2 charge. It is least penetrative, can be, see, it is like a, you see the sumo wrestlers of Japan, very energetic, very heavy, but very lethargic also. Okay, so they cannot travel too much. Even in air, they cannot travel more than 7 centimeters. They will die. Okay, though they are very energetic, but their penetrative power is very, very less. They can be stopped by a thin paper sheet. They will not be able to cross a paper sheet. Then there is beta radiation, which, as I told you, they are essentially electrons, but they are not the electrons which were revolving outside the nucleus. These electrons are generated inside the atom. Once again, I am repeating, when a neutron is getting converted into proton, then to balance the charge, an electron is also generated. That electron is known as beta particle. Okay, so that beta particle is just like electrons. So naturally, its mass number is 0. Okay, and it has -1 charge, and mass, generally we say it has negligible mass, because as I had told you in the beginning of the lecture, that mass of the electron is very, 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 very small as compared to that of, so generally we, in our calculations, we will say that, okay, it is the mass of the electron is negligible in front of the mass of neutron and proton. Okay, so its penetrative power is better than alpha particle because it is lighter. Okay, it is keeping fit by remaining thin. Okay, so it is more penetrative than alpha, but less penetrative than gamma. I will be talking about gamma radiation, and it cannot be stopped by a paper as we could do in the case of alpha. So here, to stop it, you have to use a thin aluminum plate. So metal plate is necessary to stop this radiation, beta radiation. Then there is gamma radiation. It is actually, as I already told you, electromagnetic radiation, just like X-rays, and it is more penetrative than alpha and beta particles. It can be stopped only by a very thick lead plate. Okay, so lead has that special power. That is why lead is used as a shielding material in our nuclear reactors and nuclear laboratories, because it can stop gamma radiation. Okay, so much so about these 3 types of radiations. Next, then some useful terms and units in radioactivity. Half-life. Now all these radioactive elements, they will have a half-life because they are changing, they are decaying, no? They, as I told you, that tritium is decaying into helium. Okay, so that means at certain rate this will be happening. In a second, how many how many atoms are decaying. So that gives the concept of radioactivity. If per unit time more decays are happening, that means it is more radioactive. If no decay is happening, then it is not radioactive, it is a stable isotope. Okay, so that means the time in which the number of nuclei will become half, that is known as the half-life of that particular isotope, radioisotope. So that you must remember. So in one half-life, so suppose let us see there on the graph paper, there is one example given. You are starting with 100% that radioactive atoms, the atoms. Okay, let us say atoms of tritium. So 100. So in one half-life, they will become 50%. In another half-life, it will become 25%. Then it will become 12.5%. Then it will become 6.25%. Then it will become 3 point some, and like that. By 10 half-lives, you notice by 10 half-lives, it is almost looking like zero. So we have a thumb rule that we always say that if 10 half-lives of a radioisotope has passed, that means practically its radioactivity has come to zero. Okay, now what is this radioactivity? It is explained in the next para. So activity of a given amount of radioactive element is measured in terms of decays. That means in a second, how many decays are happening? Decays per second. We call it DPS, decay per second. Okay, now that decay per second, because radioactivity was discovered by Becquerel, so in his honor, that DPS has been given the name Becquerel, and that is considered as the standard international unit of radioactivity. It is called Becquerel. So 1 Becquerel means 1 disintegration per second. Okay, then but this is too small a unit. Okay, so for practical purposes, they have honored another scientist, Madame Curie. So in her honor, they have made another unit of this Curie, which is a bigger unit. So 1 Curie is equal to 3.7 into 10 to the power of 10 becquerels, such a large unit. Okay. Then there is something like specific activity. It is just like you have mass, and then you have a specific mass, or you call it density. What is density? It is mass per unit volume, isn't it? I think all of you have studied that density of a material is, or specific gravity is nothing but mass per unit volume. Okay, so similarly, the Curie per gram or Becquerel per kilogram, that is what is known as specific activity. That tells you that which isotope is more radioactive. That means equal mass. If you, as we say, by telling the density, we are able to tell which element is lighter, which element is heavier. So similarly, the radioisotope which will have more specific activity, you will say it is more radioactive as compared to another one. Okay. Next. I think this slide I will leave. I intended to remove it. I think it is not required for you. It is for professionals. So we come to nuclear fission. So what is nuclear fission? That there are certain isotopes, in fact, very few of them, not every isotope, very few of them, when they are hit by a neutron, they break. They are so unstable, they break. Okay, I think children, see, you are children of this age, and particularly in the time of Corona, you may not be going out for playing. But in our times, at least you will know there is a game. I think in Maharashtra, it is known as Lagori. In UP, we used to call it Sekantari. The game is that you pile up 7 stones one above the other, and at a predetermined distance from there you hit that assembly of 7 stones with a ball, and if it is hit, that means the party which has hit has won. But somebody has to, opponent team has to pick up the ball and hit one of those players. Anyway, I think if you know this game, it will be easier to understand this concept of nuclear fission. So here it is just like that assembly of 7 stones, that this nucleus is not very strong. So if it is hit with a ball called neutron, then it disintegrates. It breaks into 2 or 3 lighter pieces. But in the process, the difference is that in the game, when that in that game which I told you, when you hit with the ball, that no new balls are generated. But here the wonderful thing is that when you hit a nucleus with 1 neutron, normally, and when the fission occurs, normally 2 or 3 neutrons will come out. That is the beauty of this. That is why the chain reaction, I'll tell you. So some nuclei like uranium-235, uranium-233, plutonium-239, these are the isotopes. When they are hit by neutrons, these nuclei, they break into 2 or more smaller nuclei. This is called nuclear fission. In each fission, there is a emission of 2 to 3 neutrons, and it releases enormous amount of energy. Enormous means enormous amount of energy. So far, you have only studied chemical reactions. In chemical reactions, for example, one very popular reaction, combustion of carbon. So when 1 atom of carbon burns, you know, that is used in our furnaces for generation of electricity in thermal power plants, and by burning diesel, you run the car, you run the trucks, you run the aeroplanes. Okay, so what is happening? Carbon is burning, carbon or carbonaceous material is burning. So when 1 atom of carbon burns, about 4 electron volt, this is a very small unit of energy. Okay, so when we talk per atom basis, we normally use the uh, energy unit as electron volt. Okay, so when 1 atom of carbon burns, there is a release of 4 electron volt of energy. But when 1 atom of uranium-235 undergoes fission, out comes about 200 million electron volt. So that means 200 into 10 to the power of 6 electron volt. So imagine, compare that with 4 electron volt which comes out with carbon. And carbon itself, you see, when carbon burns, how much energy comes out. So this energy is even much more than that. And that is why if you don't control this energy, then it's a powerful bomb, because so much energy can be released in a very small time. And that is why, I mean, you can make an atom bomb out if you don't control the chain reaction. So if it is an uncontrolled chain reaction, it will result into a bomb. Okay, but if you are able to control the chain reaction, which I will tell you how we control, then it will slowly release the energy, because fission will happen we will allow only 1 fission at a time. So see, what basically how we control is that every time those 3 neutrons come out of a fission. So what is, first let me tell you what is uncontrolled chain reaction. So first neutron hits the first nucleus of uranium. Okay, uranium breaks down. Let us say 3 neutrons come out. These 3 neutrons will hit another 3 nuclei of uranium. So all those 3, they will break down. Okay, when they break down, each one of them will give out 3 neutrons. So now you will have 9 neutrons. These 9 will hit another 9 nuclei, and so 9 nuclei will undergo fission. So it will become 27 neutrons, then it will become 81 neutrons, then it will become 243 neutrons, I am taking more time in saying. By this time, millions of neutrons would have been produced and the whole mass would have exploded. It happens so in a very, very short time, large amount of energy comes out, large number of neutrons come out. Okay, that is why it is called uncontrolled fission. But if we can tame this, how do we tame this? It's very simple. Every time 3 neutrons are coming out, you absorb 2 of them. You eat, you kill 2 of them. Allow only 1 to go ahead. So when that 1 goes ahead, it will hit another 1 nucleus. Okay, again 3 will come out. 3 neutrons will come out. Again you kill 2 of them. Allow only 1 to go ahead. So like that, this is called a streamlined or controlled chain reaction. That means 1 by 1 only the fission will occur. That means we get enough time, all that energy which is released, we can take it away, we can remove it, and we can convert it into electricity. That I will be telling you later. Okay, so that is what is known as controlled chain reaction. So now here anyway, we were talking about nuclear fission. So materials that can undergo fission, they are called fissile, and they can be used as a nuclear fuel in a nuclear reactor. Okay, so I hope you have understood this. Let us go to the next slide. Let me tell you a little more about it. So just now I told you what are fissile materials. Fissile material, I gave you examples also. Uranium-235, plutonium-239, and uranium-233. These are the examples of 3 fissile materials. But then there are other isotopes of uranium and thorium. So materials like uranium-235, 233, and plutonium-239, they are fissile. Fine. But some materials like uranium-238 and thorium-232, when they are hit by the neutrons, they do not undergo fission. Isotopes of same element, but they don't undergo fission. But something else happens. They absorb the neutron. And then they get converted into another element. That element, whatever that new element, new isotope is born, that is fission. So then such nuclei which give birth to a fissile material, they are known as fertile. Okay, fertile material. So examples of fertile are uranium-238. For example, you hit it with a neutron, it will give you plutonium-239, a fissile material. In fact, plutonium-239 is not found in nature. So plutonium-239 is a man-made isotope. You obtain it only when you hit uranium-238 with a neutron. Similarly, thorium-232, when you hit it with a neutron, you get uranium-233, which is a fissile material. That is why uranium-238 and thorium-232, they are known as fertile materials. Okay, so much. So I think this is useful. Remember this. Now let's go to the next slide. Let us straight come to a nuclear reactor. So how do we do the controlled chain reaction? I mean, and what is, how does a nuclear power station similar or different from a thermal power station? So here I am giving comparison of both of them. So as you can see, the in the thermal power plant, it is very simple. There is a furnace. You keep on supplying enormous quantities of coal. That coal is burnt. Carbon gets converted into carbon dioxide. Lot of pollution occurs. And the energy released, as I told you, remember every carbon atom when it is burning, 4 electron volt of energy is coming out. So all that energy, it gets converted into heat. So the whole furnace becomes very hot. And there you bring in cold water. As you can see in the diagram, the blue water which is getting into inside the furnace gets heated up, gets converted into steam, and that steam, red color, shown in red color, that steam, high pressure steam comes out and is taken to a turbine, and that turbine is rotated with the energy of this steam, and electricity is generated because it is attached to a dynamo, large dynamo. Okay, and in the process, this steam which had come out, it will become cold. So that cold water is again supplied back uh, into the furnace. So like that, this water keeps on rotating, keeps on going to the coal furnace and getting converted into steam. So it becomes a carrier of the heat. Basically, cold water goes there, collects the heat, the hot water or steam comes out, that steam rotates the turbine. What happens in a nuclear power station? Essentially the same thing happens. You convert water into steam and that steam rotates the turbine. So the right hand side is everything similar, but the change is only in the left hand side. The coal furnace is replaced by a nuclear reactor. So instead of coal burning, those vertical lines you are seeing at the bottom, red colored lines, they are actually the fuel rods. So there the nuclear fission is occurring, and same concept, the cold water is going there, but here there is a difference. We become cautious. So here what is happening, there is a closed circuit of water, as you can see. It is shown in maroon color, dark red color. So in the reactor, cold water is coming, getting heated up, goes to a heat exchanger that on the top, that horizontal device which is lying, it is a heat exchanger. It goes to the heat exchanger. So very hot water is inside the tube. A heat exchanger consists of the tube side and the shell side. So the tube side contains this very hot water. It gives away its heat to the cold water which is present in the shell side, in the main vessel, that vessel you see. That the concept is very similar to how your mother cools down the milk for you. Morning, the milkman has brought the milk late. Your school bus is about to come. Of course, nowadays you people are attending online classes, but still valid. Your class is at, let us say, is starting at 7:45. The milkman brought the milk only at 7:30. Your mother immediately boils it, and you are in a hurry. The mother wants that you should have the glass of milk before you sit in the online class. What does she do? She boils the milk. Now that boiling hot milk you cannot drink. So what does she do? She puts that milk in an aluminum vessel. She knows that aluminum is a better conductor of heat. So she puts it in an aluminum vessel, and that small vessel containing milk, she keeps in a larger vessel. Huh? That it is filled up with larger quantities of cold water, that tap water, and then she rotates that small vessel so that there is a better heat transfer, and ultimately within 2-3 minutes the milk cools down to a temperature which is convenient for you. This is what is called heat exchange, and this is what that heat exchanger is also doing. So the water is taking away the heat from the reactor, taking it to the heat exchanger, where this is same thing. The tube is equivalent to that small vessel containing milk. The shell, the bigger vessel, is equivalent to the bigger vessel. So the heat is transferred. So here we keep it in closed loop. In a nuclear reactor, we keep it in a closed loop. Okay, and from there this cold water is coming. It takes away this heat. So the imagine the milk gave heat to one water. That one water gives heat to another second water. So there is another line, double line. So we call it primary coolant and secondary coolant. So here the water which is inside the reactor, it is only bringing heat from the nuclear reactor and depositing it in the heat exchanger. That is the primary coolant. And then there is a secondary coolant coming from outside. that coolant that gets converted into steam, and same way that steam comes out. Why do we do it this way? Because now here the nuclear reactor contains radioactivity. All that radioactivity is confined inside the fuel rod, not anywhere else. So by chance, if see, there are hundreds of these tubes, the red tubes which are shown, they are known as fuel bundles or fuel tubes. There are hundreds of them in the reactor. If any one of them by any chance leaks out, that means radioactivity will come out into the water. So the water will become radioactive. That radioactive water will come out in the turbine room. And so the whole setup will become radioactive. So here what we do, the water which is going inside the nuclear reactor is not allowed to go outside. That is why we are having primary and secondary coolant. So primary coolant will never leave the reactor building. It will remain inside the reactor. So even if there is a leakage, that leakage will be confined inside the reactor building. It will not come out. So that is why we are having such. And in fact, we have reactor designs where there is a tertiary coolant also. So we have that, I will tell you later on. We have primary coolant, secondary coolant, and then ultimately we have a tertiary coolant in some of the nuclear reactors. Next slide, please. Madam, I think I have already short my time. How much time do you give me?
So we can still go on for about 10-15 minutes, but we do have the
Okay,
question and answer session.
I'll finish in that much time.
All
Okay.
right, sir.
Yeah, thank you, thank you. So now let us, we have already gone to the next slide. Now let me give you a concept of natural and enriched uranium. So see, as I told you, out of uranium-238 and uranium-235, only uranium-235 can undergo fission. So only that can give you energy. Uranium-238, we have to convert it into plutonium-239, and in another reactor, we have to burn it. Okay, so if we use natural uranium as fuel, so naturally quantity of uranium-235 is only 0.7%, because the natural uranium contains only 0.7% uranium-235. So that means the reactor will be relatively larger, or if it is the same size, then it will give lesser energy. Okay, so again, I always give my examples from the kitchen. So either you can use natural uranium, then your reactor will be of a larger size, or what you can do, you can enrich the uranium. Okay, how do you enrich the uranium? Let me give you an example from the kitchen. You just now I was talking about milk. So for in the morning, your first meal is a glass of milk. That milk is natural milk. Okay, as the buffalo has given or as the cow has given. That milk you are drinking in the morning. But when your mother wants to make rasagulla, or she wants to make gulab jamun, or she wants to make gajar halwa, what does she do? She keeps on boiling the milk. What happens by that? See, milk, in the milk, again, milk is very less. Just like uranium, uranium-235 is only 0.7%. Similarly, in milk, the bulk quantity is water. Actual milk substance is very less. Okay? So what your mother does, she keeps on evaporating the water. The milk goes on becoming thicker and thicker. Okay? And then whenever she feels it is appropriate, she stops this process. So she makes the milk rich in milk. How has she done it? By removing the bulk component by evaporation. Okay? Same thing we do. We have natural uranium containing 0.7% U-235, and the rest bulk is uranium-238. So what we do, we have special plants. I will not be talking today. We have developed a technology where we can remove the bulk. So U-235 can be removed, lot of it, so that the concentration of this U-235, it will increase. So 238 you keep on removing, so 235 quantity will keep on increasing. So this is what is. So in when your mother evaporates the milk, the resultant material is known as rabdi, khoa, mawa, okay, or condensed milk. Okay, here that enriched material, we call it as enriched uranium. So normally we, for use in a nuclear reactor, we enrich it to 3 to 4%. From 0.7, we take the concentration to 3 to 4%. We have got a facility in India. We have developed it in Mysore. Okay. Next, I think I have to be a little faster. Now, in a nuclear reactor, you need certain other materials also. As I told you, the energy of the neutron when it comes out of the fission is very, very high, that 200 million electron volt. After all, it goes to the neutron. So that energy is too high. So there is a problem. You know, there is a physics problem. When you are working with uranium-235, uranium-235 does not like very high energy neutrons. It can undergo better fission if the neutrons are slowed down. So these neutrons are slowed down by using a substance called moderator. So I have defined here, moderator is used in a nuclear reactor to moderate, slow down the neutrons, bring down their energy. Okay. Examples. What are the substances which are used as moderator? Water, heavy water, graphites, etc. They are the substances which are used as, but in India, we are using only water or heavy water, okay, as moderator. That I will tell you, there are different kinds of reactors where we use heavy water and water. Coolant, I think I need not tell you, coolant is a substance which is basically transports heat from one place to another. You have got a coolant in your car, you know, in the car there is a coolant, there is a tank of that coolant. It is water-based liquid, but some chemicals are also added in that. So what is the job of that? The engine becomes hot. So it goes there, picks up the heat and takes it to the radiator. Radiator is a large surface area. You know, you see that jolly in the radiator. So there, that heat is given away to the atmosphere. Okay. So similar way, coolant is used in a reactor, as I already told you, to transport the heat from the nuclear reactor and ultimately convert water into steam, and that steam can come out and rotate the turbine. Okay, so that is what is coolant. So again, here I have given certain examples: water, heavy water, liquid sodium at 650 degrees centigrade, molten salt at more than 1000 degrees centigrade. These are the coolants used in nuclear reactors, different kinds of reactors. Then there is third one, control rods. See this, I told you what is a nuclear reactor. It is a device where controlled chain reaction is going on. How do you control it? By using, see, I had told you that concept of when 3 neutrons come out, remove 2, allow only 1 to go ahead. How do you do that? These are so small particles, they are not visible. You cannot go inside where they are. So you can't physically do it. So you do it statistically. I mean, it is not that every time you see 3 neutrons are coming out and you go with a bat and stop 2 of them. No, nothing of that sort. It is done statistically. So you introduce certain material in the reactor, which will at any given time, it will try to remove 2/3 of the neutrons. 1/3 it will allow to whatever neutrons are there, it will kill 2/3 of them at a macro level. So that at micro level also same thing will happen. Out of 3, 2 are getting killed. So how do you do that? You use some neutron absorbing materials, which are known as control rods. For example, they can be made with boron or cadmium. These boron, cadmium, they are the elements which are very hungry of neutrons. they will immediately capture neutrons, absorb them. Okay, so mostly in Indian reactors we use boron. Cadmium is also used in certain types of reactors. Now I think I can omit this. I can come to India has a 3-stage program. I think this also I will omit. You will get it in notes, as I think your teacher was declaring that all these presentations will be available. You can yourself go through. I will go to directly that pictorial slide. Now this is a slide. It shows 3-stage program, nuclear power program of India. Those 2 slides were only to explain the basis of this. So I'm directly explaining. So here we have first stage, these vertical columns which you see. So first is first stage, then second is second stage, third is third stage. So in the first stage, we have reactors in which fission of uranium-235 is occurring. Okay, so we use either natural uranium or we use enriched uranium, but the fissile material remains the same, uranium-235. So that uranium-235 undergoes fission, lot of energy is produced, and that, as I told you, electricity is generated. But what is happening to uranium-238? The bulk material is uranium-238, your fuel, whether it is natural uranium or it is enriched uranium, still your bulk material is uranium-238. Because in natural uranium, 99.3% U-238, and in enriched uranium, around 95 to 96%. So still bulk material is uranium-238. So this uranium-238 will absorb the neutrons which are available in the reactor and will get converted into plutonium. So that material, after the fuel has been used up, we remove that fuel, take it to what we call as reprocessing plant. So there we pick up, we remove the plutonium which has got converted from uranium-238. We also pick up uranium-238 because all the uranium-238 doesn't get converted. So we pick up uranium-238, we pick up plutonium-239, and we prepare the fuel for the second stage. So essentially in the second stage, we have reactors running on plutonium-239. That plutonium-239 was obtained from the first stage. Now here in the fuel, we actually put a mixture of plutonium-239 and uranium-238. We make a fuel and that is put in these reactors. Now the fissile material has changed. It is plutonium-239. So now plutonium-239's nature is slightly different from that of 235. It likes fast neutrons also. It says, let them come, I'll face them. It doesn't essentially require the slow neutrons. So that means in these second stage reactors, you don't require a moderator. Okay, but here the amount of energy produced is very, very high, and only water if you will use as a coolant, then it will not be, when you become mechanical engineers, you will learn. Those who become mechanical engineers or electrical engineers, they will learn. There is a limit up to which you can go temperature wise with water. That temperature is generally 300 to 350 degrees centigrade. But if you want to operate at a higher temperature, your efficiency, engine efficiency, they call it, that becomes better. So to operate at 650 degrees centigrade, now your coolant becomes liquid sodium. So molten sodium becomes the coolant here. So, but it is primary coolant. So this primary coolant sodium will go inside the reactor, pick up the heat, and that heated 650 degrees centigrade sodium will come, and within the reactor, it will come into contact with a heat exchanger, where in the tube side, there will be this sodium, but in the shell side, there will be water, ordinary water. So that water will pick up all the heat which the sodium has brought. Okay. And that hot water will go to another heat exchanger where again this water, heated up water, will be in the tube side of that heat exchanger and will give away its heat to another water, the secondary coolant. So now it becomes tertiary coolant. So that tertiary coolant will only go out of the reactor building and will go to the turbine room to rotate the turbine. So this is a case, the fast breeder reactor is a case where you have three coolants: primary, secondary, and tertiary. Okay. Then in addition to this thing, because India has a lot of thorium, but with thorium you cannot start a reactor because thorium does not contain any fissile material. So in order to use thorium, you put those thorium rods in these fast breeder reactors. Because here we have got plenty of neutrons. So we put a lot of thorium rods here. That thorium will absorb. I had already shown you the reaction, okay, earlier, that fertile and fissile material. So this thorium will absorb the neutrons and it will get converted into uranium-233 isotope, man-made isotope of uranium. So you will get that uranium-233. That uranium-233, again we will separate. So we will collect all these materials. We will do reprocessing. We will separate the isotopes. So this uranium-233 is to be used as fuel in the third stage. So these three stages, they have to be in this sequence and they have to be in sequence only. One stage leads to second stage leads to the third stage. Okay, I think presently this much concept is enough for you. Now let me go. I think I will, this you can go through it, you will understand because time is less. So some slides I will have to forego. This only tells that what are our first stage reactors, second stage reactors, third stage reactors. Okay, I will only now come to the status. What is the present status? In India, 22 nuclear power reactors are working, 22 of them. Out of these 22, 18 are of one type. They are called PHWRs. Now, when you go through my slides, or you can Google what is a PHWR, okay, you will come to know. So 18 of them are PHWR. The full form of PHWR is pressurized heavy water reactor. Okay. So we have these 18 reactors, another 4 reactors, 2 at Tarapur 1 and 2, and 2 at Kudankulam in Tamil Nadu. They are light water reactors. Okay, light water reactors. That means they use enriched uranium. Those 18 reactors which I told you PHWRs, they use natural uranium, but the other 4 reactors, they use enriched uranium. So total these 22 reactors, our installed capacity is 6,780 megawatt. Now here I think I can explain it to you. I think, see, you know what is watt. That I think I'm 100% sure you know. In your house, nowadays LED bulb will be normally 10 watt, 11 watt, 15 watt. Okay, what does it mean? Your geyser will be 1 kilowatt. So 1 kilowatt geyser, if it is running for 1 hour, it will consume 1 unit of electricity. 1 unit of electricity is known as 1 kilowatt hour. That means 1 kilowatt unit running for 1 hour. That much energy, 1 kilowatt hour. That is what is 1 unit for which you pay. Okay, depending upon in which state you are. Some states have started offering free electricity. Okay, so similarly, when you make electricity, that time also same quantity. Only thing is now, because you are making in a powerhouse and supplying to the entire city, so you can't, that unit is too small, kilowatt hour. Kilowatt becomes a small unit, so we go to megawatt. Megawatt is That means 1 megawatt means 10 to the power of 6 or 1 million watts or 1000 kilowatt. Okay. Next, these are our nuclear reactors under construction. 2 in Gujarat, 2 in Rajasthan, 2 in Kudankulam, another 2 in Kudankulam. So actually totally 4 in Kudankulam. Then in Gorakhpur, Haryana Anu Vidyut Pariyojana. So the place called Gorakhpur in Haryana. There is another much bigger city, Gorakhpur in UP. Okay, don't confuse with that. Nowadays in TV they take that name quite a lot because some elections are going on there. It is not that Gorakhpur. There is a smaller place called Gorakhpur in Haryana. Okay, so that again 2 reactors are under construction, and of course a second stage reactor is under construction at Kalpakkam in Tamil Nadu. So total these, how many? 8 plus 1, 9 reactors are under construction. Their installed capacity is going to be 8,700 megawatt. So I think by 2025, we will have this 8,700 plus 6,780, which is already operating. So we will be crossing 15,000 megawatt in another, let us say, 3 years. By 2025, all these reactors will be ready. Okay. Of course, we have much larger plan than we have sanctioned projects. So in future, these more 7,000 megawatt power stations will come. In addition to that, we have so presently, what is the situation? Capacity in operation is 6,780 megawatt. Capacity under construction is 6,700 megawatt. Capacity which has been accorded, sanctioned by government is 9,000 megawatt. So totally, when all this are made, let us say by 2031-32, we will have 43 reactors and our installed capacity would reach 22,480 megawatt. So that is the status. And then we have plans for new sites. These are the where in future some more reactors will come. That's a little longer plan. I think I thank you with that. I hope it has been useful for you. Thank you very much.
Thank you so much, sir. Thank you for running us through all the practical applications of atomic energy and also for sharing examples from the kitchen. I think that is something that we can always use to remember it better in the future because it's you've simplified it to the level that the students need. And we are also made more aware of how we use it in our day-to-day life. So thank you so much for that, sir.
Yeah.
We'll quickly move on to the question and answer session.
Surely, surely.
I do have questions from the chat box that I've taken from earlier.
Yeah.
So I would just like to call out the name of the student. I request the student to please introduce yourself with your name, your school, and then post your question. All right. So our first question is from Satya Aditya. Satya Aditya from class 8, DAV Public School, Hyderabad.
Yes, ma'am, it is me only, ma'am.
Yes, please pose your question.
Hello, sir. I'm Satya Aditya of class 8, DAV Public School, Hyderabad.
Satya Aditya, ask your question.
Sir, I learned that sun generates the light and heat by nuclear fission and fusion process. And I even learned that light is made up of energy particles called photons.
Yeah.
Sir, so my doubt is that how is this nuclear fission and fusion in the sun is releasing the photons in the light which we get?
Yes, very good question. See, first let me tell you, in the sun, it is only the nuclear fusion which is occurring. There is no fission happening there. It is fusion. Today I did not talk about it. like today I told that very, very heavy elements, very heavy isotopes like uranium-235, plutonium-239, when they break, they release a lot of energy. Similarly, at very light end of the periodic table, when very light nuclei, they fuse with each other. They fuse into each other and make a heavier nuclei. That is known as fusion. So it is just opposite of fission. In fission, it is breaking into smaller particles, while in fusion, the smaller particles are joining to make heavier particles. Okay. So for example, I can just tell you that hydrogen fusing together to make helium. Okay. That is what is going on in the sun. Okay. Now, there in the sun, there is no electricity plant. Okay. So what happens there is it is made up of basically hydrogen, and that hydrogen is fusing together to give helium. Okay. Now that whole mass, because there is no coolant available there, so that entire mass, it heats up all the substance present in the sun. So it becomes, see, you must have seen at a welder's place where welding is happening, you will see that when he is doing the welding, those yellow and white sparkles come out. What are those sparkles? Extreme heat has been produced, so those particles start shining. Similarly, you must have heard terms like red hot, white hot. So when you heat certain substance at a temperature, it will become red hot. You further heat it. See, for example, the old bulbs, the filament bulbs. I don't know whether your generation is able to see them. Still, they are there. Yeah, some places they are there. So those tungsten filament bulbs. So there, what is happening? With the electricity, you are heating that wire. That wire becomes white hot, and it starts emitting light photons. Okay, because of extreme heat. So similarly, sun itself is generating the heat, and with that heat, since there is no coolant available, you are not removing the heat from there. So the entire mass present at the sun it becomes white hot, and it starts emitting those photons. Okay, am I clear?
Thank you, sir. Thank you, Satya Aditya, for that question. It was a very, very good question. Our next question is from Garima Gupta. Garima, can you please unmute yourself and pose your question?
Hi sir, my name is Garima Gupta. I am from class 8, Kendriya Vidyalaya, NET Alwa. My question is that how does the nuclear fission of uranium and plutonium form atomic energy? And is it only formed by radioactive materials? And can atomic energy be formed with the nuclear fission of any other radioactive materials like polonium or radium?
Yeah, I will tell you. See, for practical purposes, the three fissile materials I told you, one is uranium-235, another is plutonium-239, and another one is uranium-233. Practically only these three fissile materials are there which can be used, but there are some other fissile materials, but they are not available in large quantities. Theoretically you can say that they can undergo fission, but for practical purposes on an industrial scale, we can use only these three materials, and out of these three also only one is natural, uranium-235. Other two are man-made. Okay, so only, and you don't confuse between radioactive materials and the fissionable fissile materials. See, when these nuclei are slightly unstable, on their own they disintegrate. They don't wait for a neutron to come and hit them. So they on their own they disintegrate, and they don't disintegrate into two nuclei. they disintegrate into one nucleus plus another small particle. I mean, but tomorrow you will question me that when alpha particle comes, there are still two particles coming out. Alpha particle is after all helium nucleus and another nucleus is formed. So except that emission of alpha nucleus in a fission, only 2 fragments are coming out, or sometimes there will be 3 or 4 fragments also. While in radioactive decay, it is only one nucleus gets converted into another one nucleus, and in that process, a alpha particle, beta particle, or gamma rays, they come out. So radioactive materials are different. For fission, there are, and radioactive, there are thousands of radioactive isotopes available. But fission, it's a very special quality. And in nature, there is only one nucleus. And as I told you, 2 are man-made.
Thank you, Garima, and thank you, sir. Our next question is from Sohini. Sohini Chattopadhyay, can you please unmute your mic and pose your question?
Yes, ma'am. Am I audible?
Yes,
Yes.
yes.
Yes, sir. Sir, my question is that if nuclear people working in nuclear power plants have ARS or acute radiation sickness from working there, or do these symptoms come only after the disasters like Chernobyl and Fukushima occur?
Okay. Okay. Child, you tell me, what is your name? Sohini.
Yes, sir. My name is Sohini Chattopadhyay.
Yes,
I'm
Sohini.
from class 6, MIT International School, Noida.
Very good. Your question is very good. See, now I will ask you one question. You keep your mic on, okay? I will ask you one question. Have you got a gas stove in your house? Gas
Yes, sir.
stove. Gas
Yes, sir.
stove
There is
in
a gas
your
stove.
house, okay, in your kitchen. Have
Yes,
you
sir.
heard, many times you must have heard, you must have read in newspaper, or you must have seen in television that the gas cylinder bursts and the house is on fire. Why don't you tell your mother to remove the gas cylinder from the house, not use gas?
Yes, sir, because there is a very little chance of that occurring in our house as there is a gas stove.
There is still lesser chance. See, I'll tell you, whatever that little chance of that occurring in your house, there is a still much lesser chance of Chernobyl kind of thing happening in a nuclear reactor. Nuclear reactors are operating for last 50 years. There are about 450 reactors operating in the world for last 50 years. And only one Chernobyl happened. Fukushima is not an accident. I mean, Fukushima was a natural calamity. So, and then there was another 3 Miles Island, which you
Sir.
say,
In Pennsylvania, yeah, US.
yeah, 3 Miles Island in US. So that accident also occurred, but there nobody died. No radioactivity came out into the open. I mean, something went wrong, but then the design of the reactor was so wonderful that nothing happened. While Chernobyl, yes, it was an accident. Fukushima happened because of a, see, if you talk of Fukushima, nothing got it. The trains which are supposed to run on the tracks were found in the sea. The ships which were supposed to float on water, they were found inside the cities. And flyovers which were supposed to remain sturdy, they were found to have fallen down. So that was a natural calamity. These accidents are, I mean, there is a name given to them, beyond design basis accident. That means you designed something, but it did not work. In the natural calamity, it did not work. I have made a house. Under normal circumstances, my house is wonderful. It is standing very fine. But suppose tomorrow some flood comes or some earthquake happens or some high tides come. I'm not very sure how my house will stand that. But if I have to make it that strong, the cost of my house will go up. So, but anyway, I can only tell you, you are too young. I only wish that you still pursue, you learn things in this nuclear field, and statistically only I am telling you, see in the world you will find that every day some cylinders will be bursting somewhere. So those chances are more, while an accident happening in a nuclear reactor is much lesser chance. And that is why you are able to count. You tell me, can you tell me the number? How many cylinder bursts have happened in the kitchens? Let us say only in Kolkata. Can you give me the number?
Yes, sir, we can't tell that because there are
Can't
many
tell that.
happening.
But what is your gut feeling? In last 50 years, let us say, more than 50 cylinders, more than 1,000 cylinders, more than 5,000 cylinders might have burst. Okay? But you don't know the number because the number is very large. While in case of nuclear, you have the statistics of the entire world. There are only 3 accidents in 50 years. Okay? So my child,
Yes.
you should understand what is the chance. Okay?
Yes, sir.
Yeah.
Okay, sir. Thank you, sir.
Thank you, Sohini. Thank you, sir. Our next question is from Diya Patel. Diya, if you can please introduce yourself, your school, and your class, and pose
Good
your
evening,
question.
sir. I'm Diya Patel. I'm studying in 8th standard in Nirma Vidya Vihar, Charuri campus, Ahmedabad. My question was that during atomic explosion, we know energy is released. So what can be the possible reasons for energy being released?
That's what I told you. See, you have no coolant. You are talking of atomic explosion.
Yes, sir.
Okay. In any, see, what is an explosion? First, you should, I advise that you find in Google, what is the definition of an explosion? Now,
Sir, it means that a bomb explodes when the atoms are split.
No, I'm talking of explosion in general. Now, don't bring in atomic explosion. I only want you to understand what is an explosion. Explosion is release of large amount of energy within a fraction of a second. All of a sudden, the energy is released. That is what is explosion. Okay. Just now, I think the previous child, when she was asking the question, I was talking about the cylinder burst. So cylinder contains certain amount of gas. That gas gets, it catches fire. So the entire, see, normally when you are cooking, the gas is coming in a very controlled manner and only at the tip, that means on the gas stove, it is burning. But when something goes wrong, that fire travels up to the cylinder and the entire mass present in the cylinder that catches fire and the cylinder bursts out. So the amount of energy which was to be released in 1 month, because generally the gas cylinder will last for a month in a typical family. So the energy which was supposed to be released in a month's time, that gets released in 1 second. That is an explosion. Okay. So similarly, now let us come to atomic explosion. As I told you, I think if you remember, I told you 1 neutron hits 1 nucleus, then 3 neutrons come out. These 3 neutrons hit 3 nuclei, then 9 neutrons will come out. They will hit 9 nuclei, so 27 neutrons. Every time it is happening in one fission, 200 million electron volt of energy is generated. Okay. Now go on multiplying that, how many millions and trillions of electron volts of energy. It will, as I told you, it was taking time for me to tell you, but this all will happen in a second. So in a second, when this millions of electron volts of energy is released, so since we are not able to transfer this energy and convert it into some other forms of energy, it simply, this energy comes out and does the devastation. Satisfied? Okay. Next.
Yes, sir. Thank you, sir. Our next question is from Kashyap. Kashyap, if you can please unmute your mic, introduce yourself and your school.
Yes, teacher. Good evening, sir and ma'am. I'm Kashyap from 7E, St. Andrews, Secunderabad, Bovinpalli. My
Yes.
question is, can atomic energy meet the energy requirements of the entire world and put an end to our dependency on fossil fuels?
Yes. Very good question. Fantastic. I congratulate you for this question. Yes, my answer would be yes, but it should not be done. See what is happening. There is problem of global warming. So as you very rightly said, our purpose is to get rid of the fossil fuel. Okay, the energy based on fossil fuel, where carbon dioxide is produced, which is increasing levels of carbon dioxide are giving us the problem of global warming. So our purpose is to do away with fossil fuels. Now we have other smarter solutions also available: solar energy, hydroelectric power, wind energy, the entire gamut of what we call as renewable energy. Okay, so my answer to your question is that nuclear energy, along with all the renewable, in fact, it should be the other way. First, you see in a given country or in the entire world, whatever is possible by renewable sources of energy, first produce that electricity. Whatever is required more than that, because this is a fact that renewable energy alone will not be sufficient for providing the electricity needed for the entire world. Okay, so there will be a shortfall. So in fact, I always give a statement that renewable energy and nuclear power with hand in hand, while complementing and supplementing each other, that is the solution. Together, they should kick away fossil resources. Okay?
Yes, sir. Thank you, sir.
Yeah.
Thank you so much, Kashyap. And we move on to our last question. Our last question is from Syed Rahil. Can you please unmute your mic and introduce your school? All right, I think he is unable to
Okay.
mute his mic, sir. So we'll move on to the last question. I'll take another question. Tejas, can you please unmute your mic and pose your question?
Yes, ma'am. Good morning, sir. Sir, this is Tejas Chattopadhyay. Sir, I study in class 7 and I'm from NPS Whitefield, Bangalore. So my doubt is like many scientists have made their own atomic models, like in the previous years also, like J.J. Thomson, Rutherford, Bohr, and others. And the recently proposed model was by Schrodinger's wave equation. So how can the Schrodinger wave equation help us to identify what is the electronic structure and how does the electron move inside the inside the atom, and how is it beneficial?
See, very good question. I think you are studying a lot, more than what is required. So anyway, I'll answer your question. See, Schrodinger equation, you took a name Schrodinger equation. And by the way, let me tell you, J.J. Thomson only discovered electrons.
Yes.
Okay. He did not give a model for the atomic structure. The first model for atomic structure, I mean, in the recent times, was given by Rutherford, and then which was modified. There were some. See, this is all scientific discovery is always an evolving process. Okay. See, what you learn in first standard is useful when you go to the second standard. So slowly, see, your syllabus is slowly built up. Okay, and by the time you will become postgraduate, you will be a very highly learned people. So you tell me, first thing is it possible for a child of KG or of first standard to understand everything which is taught in post-graduation?
No,
Can
sir.
we jump classes?
No, sir.
For normal people, we cannot jump. Okay, we have to go through the process. Similarly, the scientific discoveries are an evolving process. If, let me assure you, if Newton had not discovered the three equations of motion, now three equations of motion are of no use when you are studying atomic structure. But still I can tell you, if Newton had not discovered the three equations of motion, I can assure you this nuclear fission and theory of relativity, they would not have come. Because, so this is an evolving process. And now coming to Schrodinger equation is a mathematical equation which is only, it helps us to analyze a wave function, because this dual nature, since you asked, I am forced to, I feel pity that I am telling so much, but then you have asked the question. So there is a dual nature of particles, that wave nature. And see, still it is not very clear whether electron is a particle or a wave. They say it is both. Okay. And in fact, for your information, I am telling you, much after the Schrodinger equation, now there are even many more theories. Density function theory is also there. Density state functions. Okay. Those theories, they are only to predict that how the electron moves actually. It has nothing to do with the nuclear structure. The Schrodinger equation, etc. It has to deal with only the electronic structure in the atom. Okay, only the electronic structure. So these are only evolving things. Yes. See, earlier somebody had told atom is the smallest indivisible particle. Then people could split atom. Then they said these neutron, proton, etc. are fundamental particles. They cannot be broken down. But now there are theories that even neutron, protons, etc. are made up of various kinds of particles, which I do not want to confuse you right now. So even neutrons, protons, they are not non-divisible particles. So these things are evolving. And as our understanding becomes better, as we take the 7 steps on a ladder, we are ready to go to the 8th step. So it is something like that.
Yes, sir.
Thank you so much, sir. That brings us to the end of our question and answer session. So thank you so much for spending time with us today, for explaining the basics, and even taking the trouble to answer almost every question that the students had on atomic energy. And like I said earlier, for your kitchen examples is something that we will all remember. Thank you so much, sir, for joining us today.
I would like to say something. I think there are still, I think children have asked a lot of questions, but naturally you have the constraint of time. So I am telling you, if these questions you can send to me, I can answer them and then you can put them on your, it will be impossible to reach out to the individual students, but I think you have a website or something, so that you decide. If you send their questions to me by email, not immediately, because I also have my own program, but I assure in a due course of time, I will answer those questions. I will send the answers to you. Now, how you propagate them to the students, you know better.
Thank you so much, sir, for being so helpful in assisting us in that. In fact, that was going to be my next assignment, an announcement as well. We will be taking all the questions from the chat box from all our sessions. For this particular session, we will consolidate and we will send it to you. And as soon as you are done answering it in your own time, based on your convenience and availability, we will post it on our website. so that every question is answered, because there are fabulous questions in the chat
Oh,
box,
yes.
extremely reflective.
Yes, yes.
And I did enjoy reading the questions, and it is unfortunate that we can't read them all out or answer them right here, but thank you for offering to address them. And students, please remember that we will be posting the answers on our website, so ensure that you keep checking the website also. All right. Before we end our session today, please let us know your comments. You can like, share, follow us on our Facebook page. You can review it. I would request you to do it after the session. So again, if you have any discussions, if you have to share your ideas on what you learned today, please go ahead and do that. And also review the session. Your next session will be on the 20th of February, which is a Sunday at 11:30 a.m. All right, and our topic for that day is astronomy from space, and Dr. Madhavan Nair, who is the former chairman of the Indian Space Research Organization, will be your keynote speaker. I know a lot of you are specifically interested in this specific topic because most of the questions in our previous sessions were about astronomy. So we hope to see you on Sunday. All right. Thank you so much, sir, for joining us once again, and have
Thank
a
you.
good evening.
Thank you, and all the best to all the children. Yeah. Okay. Thank you.
Thank you, sir.